Hi everybody, this is another walkthrough of, this time it's the Higher Physics 2015 paper. Multiple choice, questions 1 to 12, covering our dynamic universe and a bit of particles and waves. There's your datasheet right at the beginning, and the first 10 questions will be our dynamic universe. It's graphs of motion to start with. And question 1 says the following velocity time graph represents the vertical motion of a ball. Which of the following acceleration time graphs represents the same motion? Well, there's a negative gradient all the time. So there's a constant negative acceleration. So which one of our choices has got a constant negative acceleration? It can only be answer C. Answer C is the only one that has a constant negative acceleration. Let's have a look at that velocity time graph again. So yeah, for the first part, for the first 2 seconds, it's slowing down in the positive direction. So it's got a negative acceleration in the positive direction. And then between 2 and 4 seconds, it's speeding up in the opposite direction. So it's got an acceleration in the negative direction. Pretty tricky start. Constant negative gradient. So for these questions, just look at the gradient. The gradient of the velocity time graph is the acceleration. Right, question 2, this is equations of motion. A car is travelling at 12 metres per second along a straight road. The car now accelerates uniformly at minus 1.5 metres per second squared for 6 seconds. So it's decelerating, and we need to work out the distance gone. That's the same as the displacement, so it's a two-vas question. Equations of motion. Let's pick the right equation we need. Hold on, let's put our values in first. Initial speed was 12. The acceleration, but it's slowing down, is minus 1.5 metres per second squared, and the time was 6 seconds. And we're looking for S. We're not interested in the final velocity, so we want to look up our relationship sheet for one of the equations of motion that's got S, U, A and T in it. It doesn't have V in it. You'll get a relationship sheet on the website, and there they are there. Those are the relationships we need to choose from. We're going to use S equals ut plus a half at squared. It's S we're looking for, so let's substitute our values in. U was 12, T was 6. Let's keep that bracketed. Plus a half of minus 1.5 times 6 squared. Now we can simplify that. 12 times 6 is 72, minus, if you do all that on your calculator, you get 27, and 72 minus 27 is 45. It's a minus because it's a negative acceleration, so 45 corresponds to B, answer B. Question 3. This is force on a slope, a mass resting on a slope, and which row in the table shows the component of weight acting down the slope? Well, remember, we always suggest that you remember the relationship for force on a slope. The force down the slope is equal to mg sine theta. And so the force at right angles to that into the slope is mg cos theta. So which of our answers then corresponds to the row in the table that we're looking for? We want the force down the slope to be mg sine theta, and normal to the slope we want mg cos theta. So it can only be answer A. Remember, the word normal means at right angles to a surface. Okay? Now we suggest you just remember that relationship, because deriving these two force down the slope, force into the slope relationships depends on a wee bit of trigonometry. Weight always acts straight down. Mg acts straight down. So if you draw a little right angled triangle like this, then the adjacent side of the triangle is mg cos theta, The opposite side is mg sine theta. So mg sine theta for down the slope, mg cos theta for into the slope. Question 4. A person stands on bathroom scales in a lift and the scales show a reading greater than the person's weight. So the lift is moving. Let's draw a lift. Let's draw a wee guy in the lift. Now, he's got a weight that acts downwards. And his real weight is mg. If the scales are showing a greater reading than that, then the scales must be exerting a bigger upwards force on the guy. So that means that there must be an unbalanced force upwards. So the lift could be accelerating upwards. But that's not one of the answers. Upwards with an increasing speed. So we need to think about this a wee bit in more detail. It's definitely not going upwards with a constant speed. That lift is going to be accelerating. If the forces are unbalanced, it's accelerating. So it's not moving upwards with a constant speed. And it's not moving downwards with a constant speed. If it was moving downwards with an increasing speed, then the weight would have to be bigger than the upwards force. So that's wrong as well. Is it going downwards with a decreasing speed? That's correct. And it's not going upwards with a decreasing speed. Now, it's decelerating downwards, which is the same effect as accelerating upwards. You need an unbalanced force upwards to get it to decelerate downwards. Remember, upwards with an increasing speed was not one of our options, but the opposite of that will be. Downwards with a decreasing speed. That's tricky. Question 5 is about connected systems. This is a car connected to a caravan, and assuming that friction is negligible, we have to calculate the tension between the car and the caravan. Now the tension is pulling the caravan. It's only the caravan that the tension is pulling on. So we've got a car with a mass of 900, caravan is 400, and the whole system's accelerating at 2 meters per second. So if we just want to work out the tension, that's the force pulling on what's behind the tension. Then we use F equals ma, but we can use it in the form of T equals ma. Remember, the tension only pulls on the caravan. So T equals ma, the mass of the caravan was 400, the acceleration of the whole system was 2, so that's 800 newtons. Answer C. Right, on we go. Question 6. Water is flowing at a rate of 6.25 times 10 to the 8 kilograms per minute over a waterfall, and we're told the height of the waterfall. What's the power delivered by the water when it falls through 108 metres? Blimey, this is about power and energy. Let's write down what we know. We know the mass of the water per minute. We know the time is 60 seconds. We know the height is 108 metres. And we have to work out the power delivered by the water. Now, there's no relationship that links all of them, but really, if we think about our National 5 relationships, power is energy over time, and the water will have potential energy when it's at a height of 108 metres. And we can work out that potential energy because we know the mass. The mass of the water was 6.25 times 10 to the 8. G is 9.8 on Earth, and the height is 108 metres. So that'll tell us the potential energy of the water at that height. Now we can use our power equation then, because if that mass of water falls per minute, then that amount of energy will be converted into kinetic energy per minute. So let's use P equals E over T and use the total energy that we calculated. and divide that by 60 seconds. And we'll get the energy produced per second. That's what power is. 1.10 times 10 to the 10 watts corresponds to answer B. Don't forget, you could still get asked about your national 5 relationships in a higher paper. This is question 7. Looks like special relativity and length contraction here. A spacecraft is travelling at 0.6 times the speed of light, and an observer on the moon measures the length to be 190. What's the length of the spacecraft measured by an astronaut on the spacecraft? So we want the real length, the proper length of the spacecraft. We go to our relationship sheet, we find the length contraction relationship, and again make sure that you copy it down correctly. L dashed equals L times 1 minus V over C all squared. Don't forget your square root sign. Now, we want the length as measured by the astronaut on the spacecraft. That's the proper length that we're looking for. Not the observed length, the proper length. That's that L there that we're looking for. Because we know that the observed length is 190. And the observed length is shorter than the proper length. So the proper length has to be either C, D or E. It has to be longer than 190. But anyway, let's put the numbers into the relationship and see what we get. Remember, the trick here is that V over C, if V is 0.6 C over C, the C's cancel out and it just becomes 0.6 squared. So 190 equals the proper length times the square root of 1 minus 0.6 squared. I would do the bracket bit first, square root it, and then do 190 divided by that. 190 divided by square root of 1 minus 0.6 squared. Do that in your calculator, you get 237.5. It's a recurring number, rounds up though to 238. That's answer C. Question 8. This is the Doppler effect. A siren on an ambulance is emitting a constant frequency of 750 Hz. So that's the frequency of the source. The ambulance is travelling at 25 meters per second towards a stationary observer. So first things first, let's look up our Doppler effect relationship. That's it with the F0 at the beginning. The observed frequency is the actual frequency of the source times the speed of sound over the speed of sound plus or minus the speed of the source. Now the tricky thing about this relationship is the plus or minus sign. What are we going to use, the plus or the minus sign? Well, it's coming towards us, so we are going to observe a higher frequency, and to get a higher observed frequency we have to use the minus sign. Let's substitute the numbers in and you'll see what I mean. So the frequency of the source is 750. The speed of sound that we have to use is given in the question, that's 340. So it'll be 340 divided by 340 minus the speed of the ambulance, which was 25. And if you do all that on your calculator, you will get 809.52 blah 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 blah. It's a recurring number. Round up to 810 Hertz. Corresponds to answer E. Question 9 is the standard model. The emission of beta particles in radioactive decay is evidence for the existence of, well, it's neutrinos, because every time you get a beta particle emitted, you get a neutrino emitted as well to balance the momentum before and after the beta particles emitted. Question 10. Two parallel metal plates, X and Y, in a vacuum have got a voltage across them. So this is the electric fields. And an electron, there's our little electron, is fired from X to Y. So the field does some work. W equals QV is our relationship. And that electron will then gain energy in the form of kinetic energy. and its kinetic energy is a half mv squared. Now, the symbol for an electron, sometimes we don't use a capital Q. Capital Q is usually used for a quantity of charge, but for a single electron, you can either use a small q, or in this case, we're going to use a small letter E. E is used for the charge on a single electron. So instead of QV, we can write EV equals a half mv squared, and then rearrange it for the speed of the electron. So take the 2 up, take the mass down, that'll be equal to v squared, and square root both sides, and we will get our expression for the speed of the electron. Square root of 2ev over m is answer B, root 2ev over m. Right, nearly there. Question 11. Oh, this is another electric field. So when a voltage of 2 kilovolts is applied across two metal plates and an electron is fired between them and follows the path shown. This is a triple statement question. We have to decide which of those 3 statements is or are correct. Let's read them. Increasing the speed of the electron could allow the electron to reach the screen. Well, if we fire it faster, then it will pass through the field in a shorter time. So yes, it will then be allowed to reach the screen. So I think yes, that's right. Fire it faster, it will reach the screen. Statement 2, increasing the voltage. No, that's wrong. If you increase the voltage, it will be even more attracted to the upper plate. So hit the upper plate faster. And reversing the polarity of the plates just means it would hit the bottom plate. So that's wrong as well. So it's only statement 1 that corresponds to answer A. And the final one we're going to look at here, this is a fusion reaction between 2 hydrogen nuclei, heavy hydrogen. They fuse to make helium, and we're told the mass of the particles before the arrow and after the arrow. There is lost mass. There is mass that has been lost during the fusion reaction, and that lost mass is changed into energy using the relationship E equals mc squared. Now you have to work out the lost mass to subtract the smaller one from the bigger one, and you'll get 0.004 times 10 to the minus 27, and multiply by the speed of light squared. Don't forget to square it. Do that in your calculator. You get an answer of 3.600 times 10 to the minus 13 joules. And that corresponds to answer D. Right, we're going to leave it there, and we will come back to this paper a little bit later on in the year. That's the 2015 multiple choice paper. Remember, what you should really be doing is trying these questions first, and then coming and looking at the solutions about how to do them. The usual tips: use as much scrap paper as you like to arrive at your correct answer. Double check your calculations. Okay, we'll see you in the next one. See you in a bit.